fundamental theorem of calculus. In the video, this is titled Part 1, and that's not because usually I title it that way because there's 2 parts to the video. This time it's because this theorem, this idea, has 2 pieces to it, and this is the first piece of it. So we'll talk about the first part of the fundamental theorem of calculus today, and then we'll talk about the second part of it next week. So the first part of the fundamental theorem of calculus, the basic thing that this theorem says is that derivatives and integrals are inverse operations. They undo each other. And so you'll notice that we are defining a function as the integral, and then basically say that if we take that integral and want to know what the derivative of it is, then that will say that we are taking the derivative of the integral and we will wind up back where we started. So if I want to know what the derivative of the integral is, that's just going to be the original function. And the only other thing that we need to keep in mind is the bounds of the integral and what we're taking the derivative of. Because you'll notice that here we have a t, but we are taking the derivative with respect to x. It's going from a number to x, and so then x ends up being the variable. So there are going to be 2 things we're going to need to keep in mind when we do these problems, because otherwise they're going to be really, really simple. The first is that we need to make sure that we are using the correct variable, and that's whatever we're taking the derivative of, or the bounds of the integral. The second thing is that we will still, on some problems, have to worry about the chain rule. And if we have a more complicated function, then the bounds of these integrals have to worry about the derivative of the inside part. But let's do some basic examples here so that you can see what this looks like. All right. These first ones, the idea is going to be as long as you are just taking the integral from a number to x, as long as we're just working from a number to x, then all we need to do is, instead of whatever variable it says, usually a t here, instead of the other variable, we're going to put an x here, but we're going to keep the original function the same, and that's going to be our answer. So these are going to be really easy. Because what we're doing is we are saying find dy dx. In other words, give me the derivative of the integral of sine squared of t. Well, the derivative of the integral of sine squared of t is going to be sine squared of x instead of t. So all we're doing, as long as it's just a number to x, all we're doing is that we are taking the function and putting an x in instead of t. So guess what? This one is going to be 1 plus x over 1 plus x squared. Done. Let's do the next one and feel really smart. Because we are mixing differentiation and integration and we're knocking it out of the park. From a number to x, so all we need to do, wherever there's a t, we're going to put an x. Done. Remember, the idea here is that we are taking a derivative of an integral. We are basically doing the equivalent of taking a number, multiplying it by 5, and then dividing it by 5. And saying, hey, we wound up back where we started. Well, yeah, that's what multiplication and division do. They undo each other. Same thing with differentiation and integration. They're going to undo each other. Genius. So smart. Questions so far? All right. Here's a bit that's going to get a little bit trickier. So I said thing number one you have to worry about is making sure the variable matches the bounds of the integral. And thing number two is if you have something other than x in the bounds, like an x squared or some other function in the bounds, then that needs to play into our integral here. So we are working from 0 to x squared now. So we're going to write this upper bound into our equation here. So instead of t, now the thing that goes in here is the x squared. And then because we have an x squared in the bound, we need the chain rule to multiply by the derivative of the inside part. The derivative of x squared is going to be 2x. And so if we want to rewrite that, we put the 2x out in front, and then x squared squared is going to be x to the 4th. So, not quite as basic as what we were doing, but still nothing too insane. Next one. Derivative of the integral, except instead of u, I'm going to put what? 5x. And we're using 5x because it was this upper bound. So we're putting the 5x wherever that u happens to be. So that's not all we're going to do because we also need the chain rule. Times the derivative of the inside part, derivative of 5x.
So you just
It's 5.
You just get rid of the square root?
No. We write the square root. I just didn't notice it was there. So we wrote the same function, except instead of wherever there's a u, we put a 5x to match the bound, times 0 to the inside part. All right. There's a problem with this one. What's different about this one?
Going from X to a number.
Going from x to a number instead of a number to x. But we can fix that. We can just change it and switch it from t to the dt. So I haven't done the derivative yet. So we can switch that if, trying to find out if you watched those yesterday, if we do what? What did the property say that we have to do? Look at your notes from yesterday. If we are going to switch those bounds, there was something that we had to do. So if I switched from A to B to going from B to A, make it negative. We talked about why that was yesterday. But this is a situation where it's going to be helpful for us to switch those bounds instead. And so all we need to do is make it negative. And now it's just from a number to x, so we still have that negative out in front. And then we don't need to worry about the chain rule, so there's our answer. So give H a try here. First thing we want to do is put the variable on the top. Not bad. Is that what we got? It shouldn't be.
No.
Although I'm pretty proud of myself for being able to write this neatly without seeing it. things missing. Figure out what they are. Morning. Hi. Okay. Okay, I will work on that. If I can't get it set up by that, then on that short notice, then I can send her a message with what she'll need. Okay. Yep. Thank you. Two things.
Negative chain rule. Or negative angle.
Hey, there's a negative. When we switched the bounds, we made it negative, so it still needs to be negative. And then, what was the other thing you said?
Chain rule.
Oh, the chain rule! Times derivative of the inside part, derivative of x cubed. It's 3x squared. So if we wanted to, we could rewrite the 3x squared is on the top. X cubed squared is x to the 6th. It's a common thing I see people miss. X cubed squared is x cubed times x cubed. So that's x to the 6th. X cubed times x squared is x to the 5th. And x cubed squared is x to the 6th. Okay. I'll leave this one for people to consider how we're going to do this one. And I'll talk about it again. It's going to have to do with properties of integrals. That's my hint to you, but we'll talk about it next time. I want to get to these two questions. Construct a function of the form of the integral that satisfies a given condition. So in other words, this is the derivative what's the original? So this is going to be another question that involves thinking about our integral properties. That's going to be what's useful for us. And I think the easiest way to see this is going to be for me to kind of show you what the answer is, and then we'll reason our way for how we know that's the answer. So what's the original function? So hopefully you know that because we talked about derivatives and integrals being opposites of each other, that somehow this is going to involve an integral. If we have the derivative and we want to undo that to get back to the original function, we're going to integrate. And I'm going to explain this in a second. That's the answer. So first off, unnumbered to x for our property that we talked about. And this works, let's talk about why this works. This works because when x is 0, or sorry, when x is 5, we want to control for this. And when x is 5, oh, wait a second. Let's not keep the dt. I can't have the same thing in the bounds as I have in the integrand. So I need to just use a different variable. Check this out. From 5 to x means that wherever there's an x, I'm going to put in 5. From 5 to 5. And what is the integral from 5 to 5 of that function? This was something we talked about yesterday. How much area is between 5 and 5?
0.
None. So, integral of 5 from 5 to 5 of who cares? The answer is now 0. Questions on that one?